In this video, we'll talk about stresses in helical spring. The left side shows a helical spring subjected of force F. The diameter is capital D and the coil diameter is small d. A free body diagram can be drawn as shown. The net stress on the spring is given by T rho divided by J plus an axial force F or axial stress F divided by A. We can substitute for T and rho as D divided by 2 and J as pi D raised to 4 divided by 32, and then also substitute for capital A, it's pi D squared divided by 4. This is the expression we get once we do the substitutions. Finally, we can write an expression for the shear stress tau as Ks times 8Fd divided by pi d cube. Here Ks is the stress concentration factor or stress factor. It is given as 2c plus 1 divided by 2c, and c is basically a spring index. It's capital D divided by small d. There's something called curvature effect, which is very important when you look at stresses in a spring. Let the inner diameter of the coil be d subscript I and the outer diameter be d subscript O. The inner diameter is basically as di is d minus d and the outer diameter is do is d plus d. The length of the inner coil is n times di, where n is the number of coils. That comes out to be n d minus small d, and the length of coils on the outer side is n times d0, which is n d plus d. So what we see here is that if you unstretch the spring, then the length of the coil on the outer side is n d plus d, and the length of the coils on the inner side is n d minus d, and clearly n d plus d is greater than n d minus d. This actually causes a stress on the beam, on the spring, where it is wound in its shape. This stress can be ignored when there's static loading, but it cannot be ignored for fatigue loading. So we've seen Ks, that's the shear stress factor. There's something called Kc, which we introduced now because of curvature effect. What we can do is we can think of the combined effect of Ks and Kc through a factor which was found independently by two people, Wall and Berger-Strauss. So Kw is the Wall factor, Kb is the Berger-Strasser factor. These basically take the effect of both shear stress and curvature. Kw is given by this formula and Kb is given by this formula. You can check that these formulas are actually 1% between each other. What we're going to do in this course is going to stick with Kb, which is the Berger-Strasser factor. Kc, which is the curvature effect, can now be obtained from Kb and Ks. So Kb and Ks was written in the earlier section as follows. So to predict the combined effect of shear and curvature, we use this formula, tau equals Kb 8Fd divided by pi d cube, where Kb is the Berger-Strasser factor. Here are two formulas which I'm going to show you without any derivation. The deflection of a spring is given by this formula, and the spring rate or the spring constant is K is given by this formula. We look at some of the ways in which springs are attached. So there are four conditions here, as shown here. This one is plane end, as you can see with the helix, and that helix is at an angle. The next one is the end is actually squared, so it's flat. That angle is, you can think of it as 90 degrees or 0 degrees helix, as they call it. You could also have squared and grounded, so it is connected to the ground. So it's taking this particular spring and connecting it to the ground. And finally, you can have plane like this one and grounded. Okay. Now, for these four types of end connections, there's a table which gives you end coils, total coils, free length, solid length, and pitch. This is something which we'll be using later on when we solve the problem. There's something called set removal or presetting. This is to induce residual stresses. This makes the spring stronger. So what manufacturers do is they create a spring which is longer than usual. Then they compress it to a solid length. This sets the spring length and induces residual stresses. And these residual stresses basically are the ones which helps the springs to take care of bigger stress than what we normally put without presetting. This particular set removal of presetting is recommended for static loading, but not for static applications. This table 10.3 gives you a list of spring materials and gives you some description. It just helps you to choose different springs. Let's come to the strength of springs. If you plot the log of the ultimate strength versus the diameter of the spring on a log-log plot, then you see it's a straight line. So the equation of the straight line is y equals ax plus b. Now what we can do is, we know that y equals log of SUT and x equals log of d. So since y equals mx plus c, I substitute y equals mx plus c. So I just put these values and I remove the logarithm sign. And you can see that if you put a equals -1 divided by m and e raised to b is equal to a, then SUT is a divided by d raised to m. Now this is something which has been empirically found. It has not comes from first principles. How do you compute A and M? There actually is a table. Here's a table. This table basically gives you values for A and values for M. So if you know the type of wire, for example, music wire, you know what M is, you know what A is, and since you know the diameter of the spring, which is something which you can measure, you can now compute the ultimate strength SUT. Many times we're interested in yield strength. Here the yield strength is given as a fraction of the ultimate strength. So the yield strength is between 0.6 and 0.9. We know from distortion energy theory that shear yield strength is 0.57 xy. And so using that formula in here, we can compute a range for the shear yield strength. Okay. So here is a table which gives the mechanical properties of spring wire. Okay. I talked about SY and SSY as having been between a range. This basically table will give you that. So for example, a music wire, we'll see that SY is between 0.65 and 0.75 of SUT. And then here it says SSY is 0.45 and 0.6 of SUT. Here is a table which gives you the maximum of the tensile strength before set removal and after set removal. So depending on what type of spring it is, you can use this value. So here we can actually get the shear yield strength, for example, for non-ferrous alloy, that's 0.35 SUT, and you can use that for calculations. You can use a formula we've learned here to solve for these 7 sub questions. Okay, this is a table we'll be needing. It's from the appendix A28. So for the first question, which is A20, problem A, we need to estimate the torsional yield strength of the wire. For that, what we need to do is we need to look up this particular spring. It's a number 16 music wire spring, and the outside coil diameter is given. So let's go to this table A28. So if you go and look at the gauge, it says 16. This is the one we're looking for, 0.037, because it's given in this table here, 0.037. I've indicated that in yellow. Next, what we do is we need to find the ultimate strength. So that for we go to table 10.4, as shown earlier. From that, we can compute A and M. So we know A and M, and we know the diameter. So we can compute SUT. Here it is 324 kpsi. Then we go to table 10.6. If we go back to table 10.6, right here, we know that here we are looking at music wire. Here the maximum percentage before set removal, that's what we assume, is 0.45 of SUT. So we go down and we have SSY is 0.5 SUT. So it comes out to be 146 kpsi. The next question is estimate the static loading corresponding to the yield strength. So here the formula is tau equals kb8fd divided by dq. What we are given here is capital D0, it's 7/16, and we know small d, the diameter of the coils. So we can compute the mean diameter d, we can compute the spring index c. We then compute the Burger-Strausser factor kb, 4c plus 2 divided by 4c minus 2. And then since we are told the torsional yield strength, tau is SSY is 146 kpsi. So we substitute all these values in one and solve for F. So we get F equals 6.46 lbf. Next, we are asked to estimate the scale of the spring. This is a formula which was given. The formula is scale is d raised to 4 g divided by 8 d cubed divided by na.
Now we need to get some of these values from the table. So from table 10.1, we can compute NT, which is 12, well, it is Na plus 2 here, and NT is given as 12.5. So the ends are squared and there are 12.5 total turns. That's NT, total turns NT. So given NT, we can compute Na, which is 10.5. From table 10.5, which is given here, G is 11.85. And from G, D, small and capital, and Na, we can compute the spring constant K, or the scale factor. Next, we asked to estimate the deflection. So that's again a formula. The deflection formula is given by F divided by K. F is already something we've computed, scale factor is computed. So the deflection is 1.56 inch. Next, we go to E, the solid length of the spring. So for that, what we do is we basically use table 10.1. It gives a formula for the length of the spring. LS is NT plus 1 times D. NT is something we are given, it's 12.5. Small d is something we got from the table, and so we can compute the spring length. Next, we are asked to estimate next we asked what length should the spring be to ensure it is, when it is compressed solid and then released, there'll be no permanent change in the free length. This is basically the net length of the spring. This can be obtained by simply adding the deflection y to ls. So it's 2.06. The last question, G, is what is the pitch of the body coil? We want to compute pitch, which is given by from table 10.1 is L0 minus 3 divided by Na, and putting the values to get 0.186.